Welcome to this presentation on electromagnetic neurotechnologies. In this playlist, we will explore how electromagnetic fields intersect with neuroscience to revolutionize diagnostics and treatments. We'll break down the origins of electromagnetic neurotechnology, how the integration of electromagnetic science evolved, the concept of neuroelectromagnetism, understanding how electrical and magnetic fields are generated by brain activity, diagnostic and treatment applications, how these technologies are used for structural and functional brain imaging, as well as innovative therapies. We'll also touch on specific frequency ranges and cutting-edge tools. This field is vast, and its implications for healthcare and industry are transformative. Let's get started. The story of electromagnetic neurotechnology begins with two key discoveries. 1. Electromagnetic fields. In the 19th century, scientists like Michael Faraday and James Clerk Maxwell established the foundations of electromagnetism. Maxwell's equations showed how electric and magnetic fields interact. 2. Neuroscience advances. In the 20th century, researchers discovered that the brain operates using electrical signals. The work of pioneers like Hans Berger, who developed the first EEG, demonstrated that these signals could be detected and measured. Over time, scientists began integrating these fields. By applying electromagnetic principles to brain function, they created tools to visualize and influence brain activity. This led to the development of magnetic resonance imaging, MRI, for detailed brain scans, electroencephalography, EEG, for tracking brain waves, magnetic stimulation, TMS, for non-invasive brain stimulation. Today, electromagnetic neurotechnologies offer non-invasive ways to diagnose and treat brain disorders. They have applications in neurology, psychiatry, and even industrial diagnostics, such as evaluating concrete structures. Neuroelectromagnetism refers to the study of the brain's natural electrical and magnetic fields. Our brain's neurons communicate using electrical impulses. Whenever a neuron fires, it creates 1. Electrical fields. These fields can be detected by placing electrodes on the scalp, a technique known as electroencephalography. 2. Magnetic fields. These fields are much weaker, but can be measured with MEG, magnetoencephalography. Understanding neuroelectromagnetism allows us to map brain activity, identify which parts of the brain are active during different tasks, detect abnormalities in brain function, such as epilepsy or brain injuries, develop treatments, use magnetic and electrical fields to stimulate or inhibit brain activity, helping treat conditions like depression and Parkinson's disease. This field is critical for developing both diagnostic tools and therapeutic methods, understanding of how the brain functions. Diagnostic electromagnetic neurotechnologies fall into two main categories. 1. Structural imaging, focuses on visualizing the brain's anatomy. In this category, magnetic resonance imaging uses strong magnetic fields to generate detailed images of brain tissues. And microwave imaging uses wave to create permittivity profile of the brain materials. Also, computed tomography uses X-rays to capture cross-sectional images. 2. Functional imaging, tracks brain activity in real time. In passive technologies category, these simply measure brain activity without intervention. EEG and MEG are prime examples. EEG measures electrical activity on the scalp, MEG captures the magnetic fields generated by neuronal currents. In active technologies categories, these actively influence brain function. fMRI, functional MRI, measures changes in blood flow, active brain regions. Examples include transcranial magnetic stimulation, TMS, and deep brain stimulation, DBS. These technologies are essential for diagnosing conditions like epilepsy, brain tumors, and neurodegenerative diseases. Electromagnetic fields are not just for diagnostics, they are also used for treatments. Here are key examples. Electroconvulsive therapy, ECT, uses low-frequency electrical currents, around 50 Hz, to treat severe depression. It remains one of the most effective treatments for drug-resistant psychiatric. 1. Deep brain stimulation, DBS, involves implanting electrodes that deliver electrical pulses to specific brain areas. Frequencies typically range from 120 Hz to 200 Hz, it used for Parkinson's disease, essential tremor, and OCD. 2. Electromagnetic RF, radio frequency, and microwave frequencies, 10 MHz to 3 GHz, to heat and destroy cancer cells. The targeted heating spares surrounding healthy tissue. 3. Temporal interference stimulation, uses two high-frequency electrical fields that intersect to create low-frequency stimulation. This technique could provide non-invasive DBS alternatives. Understanding these frequency ranges helps tailor treatments to specific conditions, making electromagnetic neurotechnologies powerful tools in modern medicine. In this part of the presentation, we'll discuss their principles, advantages, and limitations, providing a clear understanding of how these technologies are applied in clinical settings. We'll also explore the different methods of brain imaging using electromagnetic technologies, focusing on both structural and functional imaging. With structural imaging, the goal of structural imaging is to capture detailed images of the brain's physical structure. This is crucial for identifying anatomical abnormalities such as tumors, injuries, and malformations. The main technologies used for structural imaging include MRI, CT, and emerging techniques. The slide introduces two important concepts. 1. 3D resolution space. This graph shows the trade-offs between O time resolution, delta t in seconds, how quickly the technique captures brain activity. O spatial resolution, delta x in millimeters, how precisely activity. O contrast, delta c/c%, the ability to differentiate between different brain regions or activities. 2. Multidimensional acceptance space. This diagram highlights the factors influencing the usability of imaging technologies, such as operator dependence, training requirements, miniaturization, portability, cost, patient comfort, and harmlessness. Together, these concepts provide a framework for evaluating and choosing the right imaging technology for specific needs. In summary, the clinical scope of brain imaging encompasses a wide array of electromagnetic technologies for both structural imaging. These tools offer powerful insights into brain anatomy and activity, paving the way for better diagnosis, treatment, and understanding of the brain. Now, let's move on to structural imaging electromagnetic neurotechnologies comparison. Magnetic resonance imaging, MRI, works by using magnetically labeled water protons as tracers. When the brain is exposed to strong magnetic fields, these protons align and produce signals that are converted into detailed 3D. MRI offers high spatial resolution, making it ideal for detecting fine structural details. However, the temporal resolution is low, meaning it's not suited for real-time imaging. MRI is also expensive due to the sophisticated equipment involved. Computed tomography, CT, X-ray beam, to generate 3D images. Like MRI, CT scans provide high spatial resolution but have low temporal resolution. CT is particularly useful for detecting bone fractures and acute bleeding. However, it involves ionizing radiation, which can be a drawback compared to MRI. Microwave-based imaging is an emerging technology. This technique involves sensing temperature and conductivity changes using microwave antennas. Measuring signals reflected from tissue boundaries to generate images. Microwave imaging can detect temperature variations and blood volume change be converted to electrical signals for analysis. It offers high temporal resolution but still has unspecified spatial resolution. One advantage of microwave imaging is that it has the potential to be less expensive compared to MRI and CT, making it a promising tool for broader clinical use. Now, let's move on to functional imaging, which focuses on measuring brain activity in real time. Functional imaging is essential for understanding how different brain regions work and interact. It helps diagnose conditions like epilepsy, monitor cognitive functions, and guide brain surgeries. The primary modalities are EEG, MEG, fMRI, FNIR, and PET. Each method has distinct characteristics in terms of spatial and temporal resolution, invasiveness, and application. To summarize, these functional imaging techniques vary in their strengths and weaknesses. For example, EEG and MEG are ideal for high-speed recordings of brain activity but lack fine spatial detail. fMRI offers excellent spatial resolution but is slow and noisy. FNIR is portable and non-invasive, making it suitable for flexible clinical use. PET provides detailed metabolic information by its invasiveness and cost. Each technique is suited to different clinical and research applications, and often, combining multiple methods gives the best results. In conclusion, electromagnetic neurotechnologies represent a dynamic field with profound implications for medicine and industry. From diagnostics to treatments, these tools harness electromagnetic principles to unlock new possibilities for understanding and healing the brain. Thank you for joining this presentation. Welcome to this video on electromagnetic neurotechnologies for structural brain imaging, where we will explore the fascinating role of electromagnetic fields in advanced brain imaging techniques. Structural brain imaging is a cornerstone of modern neuroscience and clinical diagnostics. This presentation will guide you through three technologies: magnetic resonance imaging, MRI, microwave brain imaging, and computed tomography, CT. These technologies leverage unique electromagnetic principles to provide detailed insights into brain anatomy. First, we will delve into the physical background of these techniques, starting with MRI and its and RF electromagnetic fields. Next, we will explore the emerging field of microwave brain imaging, which employs gigahertz frequencies for safe and portable imaging solutions. Finally, we will discuss CT imaging, which uses high-energy X-rays and tomography for fast, accurate diagnostics. At the end, we will compare the reconstructed image characteristics of these technologies to understand their strengths and limitations. Let's dive in. Before diving into each imaging technique, let's position these technologies within the electromagnetic spectrum. The spectrum encompasses a wide range of frequencies and wavelengths, each with distinct properties. Magnetic resonance imaging, MRI, operates in the radio frequency, RF, range, around the megahertz. This frequency allows deep penetration into tissues with minimal energy absorption, making MRI a non-invasive and safe option. Microwave brain imaging works at gigahertz frequencies, offering a balance between resolution and penetration depth. Computed tomography, CT, uses high-frequency to provide exceptional resolution but at the cost of higher energy and ionizing radiation. The relationship between wavelength, lambda, frequency, f, and the speed of light, c, is a fundamental principle here. Lambda equals cf. This equation highlights how higher frequencies yield shorter wavelengths and higher resolution, which are ideal for fine structural imaging, while RF waves are better suited for deeper, non-invasive imaging. Magnetic resonance imaging, MRI, is a revolutionary non-invasive imaging technique, as illustrated by the images on this slide. In the top left, we see a cutaway view of an MRI scanner, which highlights its key components: the superconducting magnet, B0, gradient coils, RF coils, and the patient. Together, these components create a powerful system to generate detailed images of internal structures. The diagram in the top center explains how the hardware functions. The static magnetic field, B0, aligns hydrogen nuclei in tissues, while the RF electromagnetic field, B1, applied via, excites them to resonate at the Larmor frequency. After the RF pulse stops, the nuclei relax, emitting signals captured by the receiver coils, as shown in the schematic. The top right image details advanced RF coil designs like birdcage coils and resonators, which enhance the uniformity and efficiency of the improving image resolution. The conductive shield around the coils reduces interference, ensuring signal quality. In the bottom left, we see how MRI images are constructed. Tissue is divided into voxels, and the magnetic moments of hydrogen within each voxel produce signals that are mapped into pixels. Signals are processed using Fourier transforms, as shown in the flowchart in the bottom right. The data transitions from signal acquisition to K-space and finally to reconstructed images, slice by slice. Together, these images demonstrate the harmony between MRI hardware and image reconstruction processes. MRI's ability to safely capture high-resolution images of delicate tissues, without ionizing radiation, is what makes it indispensable in fields like neurology, oncology, and pediatrics. Next, we have microwave brain imaging, a cutting-edge technology that uses microwaves in the gigahertz frequency range. Unlike MRI, as depicted in the slide's top left illustrations, microwave brain imaging is portable, cost-effective, and ideal for use in out-of-hospital environments. Let's explore how it works. The top diagrams illustrate two primary microwave brain imaging methods. The first is microwave radiometry, which relies on passive antennas, as shown on the left. These antennas detect thermal radiation emitted by tissues. The signals are processed to measure temperature changes, providing insights into blood activity. For example, the thermal conductivity detected by the radiometer is proportional to changes in tissue activity, offering a non-invasive way to assess brain function. The second method, reflection analysis, shown in the middle top illustration, uses active transmission. Antennas transmit and reflections caused by tissue boundaries are analyzed. The time of flight, TOF, equation, TOF equals 2dc, calculates the distance to these reflective surfaces. Multi-antenna setups, as depicted in the diagram of sensor points on the bottom right, increase sensitivity and resolution, make it effective for detecting hemorrhages, strokes, and monitoring cerebral circulation. The inverse problem path, shown in the central flowchart, highlights the complex computations required for quantitative imaging. Scattering matrices, measured by vector network analyzers, are processed to reconstruct detailed images of the illustrated on the right. Finally, the frequency response graph on the bottom left shows how microwave systems operate across a range of frequencies to enhance detection accuracy. These advancements enable MWBI to detect conductivity and temperature changes as deep as 5 cm within brain phantoms, making it a powerful diagnostics. In summary, this slide captures the core principles of microwave brain imaging, its hardware, computational methods, and clinical applications, demonstrating its potential as a revolutionary diagnostic technology. Finally, we explore computed tomography, CT, one of the fastest and most accurate methods for brain imaging. As shown in the top left illustration, CT relies on X-rays, which are high-energy electromagnetic waves. These X-rays pass through tissues, with their intensity attenuated based on the tissue density described by the Beer-Lambert law, I equals I0 E minus mu x, where 2 is the transmitted intensity, I0 I_0 is the initial intensity, mu is the attenuation coefficient, and XX is the tissue thickness. The middle top diagram illustrates how the CT scanner works. It rotates around the patient, shown in the photograph at the bottom left, capturing multiple projections at different angles. These projections are detected by an array of sensors, as shown in the schematic of the X-ray flat panel detector. The captured signals are processed into digital data that can be reconstructed into cross-sectional images algorithms, such as filtered back projection, as highlighted in the gridding and IDFT process in the bottom right diagram. For enhanced imaging, Xenon Enhanced CT, SEI-CT, introduces xenon gas, shown in the top left image, which crosses the blood-brain barrier to act as a radiopaque tracer, improving the visualization of blood flow. However, CT has its limitations, including motion artifacts and difficulties in imaging dense regions like the posterior fossa. Together, the images on this slide demonstrate how CT combines hardware precision, like the rotating X-ray tube, and advanced computational reconstruction to deliver brain imaging. Despite its challenges, CT remains a cornerstone in clinical diagnostics. Let's dive into the comparison of reconstructed image characteristics for CT, microwave brain imaging, MWBI, and MRI, as illustrated on this slide. Each imaging technology offers unique strengths and limitations, making them suitable for different applications in brain imaging. First, let's resolution. The CT image on the left demonstrates its superior ability to resolve anatomical details, such as the sylvian sulcus and midbrain structures, making it ideal for emergency diagnostics. MRI, as seen on the right, provides excellent contrast for soft tissues, highlighting regions like the internal sulcus, making it indispensable for neurology and advanced structural imaging. MWBI, shown in the center, is advancing in spatial resolution and shows promise for functional imaging through temperature and conductivity changes. Safety is another critical factor. Unlike CT, which uses eyes, both MRI and MWBI avoid radiation exposure, as they rely on electromagnetic fields. This makes MRI and MWBI safer for repeated use, especially for vulnerable populations such as children or pregnant patients. Portability is where MWBI stands out. MWBI devices are compact and can operate outside traditional hospital settings, offering great potential for mobile diagnostics and monitoring in remote or resource-limited areas. In contrast, CT and MRI require large, stationary systems, as depicted in their respective images. Each technology also has distinct applications. CT, with its rapid imaging capabilities, is the first choice in emergencies like trauma or stroke, where speed is critical. MRI, with its ability to capture detailed structural and functional information, is preferred for in-depth studies of the brain and other soft. MWBI, while still developing, is a cost-effective and portable solution for applications such as monitoring cerebral circulation or detecting strokes in real time. To summarize, the interplay between electromagnetic fields and human tissues underpins the power of these imaging technologies. MRI frequency fields and strong magnets to create non-invasive, high-resolution images. MWBI leverages changes in temperature and conductivity for portable and safe diagnostics. CT employs high-energy X-rays combined with tomographic reconstruction to deliver rapid, precise imaging. Its strengths and complements the others in advancing medical diagnostics. Future innovations in electromagnetic technologies will undoubtedly make brain imaging more accessible, accurate, and transformative, meeting the evolving needs of healthcare. Welcome to this comprehensive exploration of functional brain imaging using electromagnetic neurotechnologies. In this video, we will cover a variety of techniques employed in understanding the human brain's activity, ranging from electroencephalography, EEG, to more advanced methods like positron emission tomography, PET, and emission computed tomography, SPECT. Each technique provides unique insights into brain function, offering unparalleled opportunities for both clinical and research applications. Stay with us as we break down the different modalities, their data acquisition, and processing methodologies. In this slide, we see how various brain imaging techniques relate to the electromagnetic spectrum. These techniques utilize different parts of the spectrum to capture brain activity in unique ways. SPECT and PET operate in the gamma-ray region, capturing metabolic activity in the brain through radioactive tracers, helping to diagnose stroke and Alzheimer's. fNIRS uses infrared light to measure blood oxygenation changes in the brain, offering a portable way to monitor brain function during real-world activities. fMRI works in the radiofrequency and magnetic regions, measuring blood flow and oxygenation to provide detailed images of brain activity. MEG detects magnetic fields from neural activity, using the low-frequency range to capture real-time brain dynamics with high precision. EEG measures electrical activity directly from the scalp, providing insights into brainwave patterns, useful for diagnosing epilepsy and studying sleep. Each of these technologies offers into brain function, contributing to a more comprehensive understanding of the brain's activity. In this slide, we examine the processes involved in EEG and MEG data acquisition and processing. These two neuroimaging techniques are both powerful tools used to study brain activity, though they capture different aspects, electrical versus magnetic signals. We begin with EEG. Electroencephalography measures the electrical activity of the brain by placing multiple electrodes on the scalp. The first step in EEG data acquisition is recording brain activity from the surface of the scalp, where the electrical signals from neurons are captured. These signals, or brainwaves, are then converted into time series data. The next, the signal by filtering out noise and artifacts, preparing the data for further analysis. This stage also includes digitizing the data using analog-to-digital converters, A/D. The processed EEG data is then subjected to advanced techniques like blind source separation, pattern recognition, and topography to extract meaningful features from the raw signals. These methods help identify patterns related to cognitive states, such as attention, relaxation, or sleep. On the other hand, MEG, magnetoencephalography, measures the magnetic fields generated by the electrical activity of neurons. The first step in MEG data acquisition is recording the magnetic signals from the brain using highly sensitive squid, superconducting quantum interference devices, sensors placed around the scalp. Sensors detect the faint magnetic fields produced by neuronal currents. Like EEG, the recorded data is processed by filtering to reduce noise. Then, the beamformer projection technique is applied, which maps the extracranial magnetic data back into the brain space to visualize the areas of the brain producing activity. The next step involves estimating the phase and amplitude of brain waveforms using the Hilbert transform. These parameters are then analyzed to study phase synchronization, amplitude cross-correlation, and other temporal dynamics, which are critical for understanding brain network activity. Finally, an adjacency matrix is a map of functional connectivity between brain regions, offering insights into how different regions interact during various tasks. Both EEG and MEG offer real-time insights into brain dynamics, but they complement each other by measuring different types of signals, electrical activity with EEG and magnetic fields with MEG, leading to our understanding of brain function from complementary perspectives. Now, we shift to magnetic resonance imaging, or MRI, which provides detailed structural images of the brain. MRI is based on the principles of magnetic fields and radio waves, offering highly detailed 3D images of brain structures without the need for any radiation. The data acquisition process involves placing a magnetic field and using radiofrequency pulses to excite hydrogen atoms in the brain. When the hydrogen atoms return to their original state, they emit signals that are captured to construct a detailed image of the brain's anatomy. MRI is invaluable for diagnosing brain conditions like tumors, strokes, and multiple sclerosis. In addition, in this slide, we see the step-by-step process of how MRI captures brain activity. First, a stimulus, like a visual cue or cognitive task, triggers a neural response, shown in the top part of the slide. This activates brain areas, increasing metabolic activity and blood flow. It illustrates how synaptic signaling and metabolic signaling lead to a vascular response, where blood vessels dilate to deliver oxygenated blood to active brain regions. The bold signal relies on changes in oxygen levels in the blood. As shown, deoxygenated blood causes MRI signal dephasing, and oxygenated MRI signal, highlighting active areas. The MRI scanner, shown below, captures these signals as case-based data, which is then processed using an inverse Fourier transform to form the final brain image. This process allows us to see which brain regions are active during tasks, with stronger signals indicating more oxygen. Through this process, MRI gives us both structural and functional insights into the brain's activity, enabling detailed imaging of brain functions in response to various stimuli. In this slide, we are exploring functional near-infrared spectroscopy, or fNIRS, which is a non-invasive optical technique used to measure brain activity. The first image illustrates how infrared light is used to detect changes in blood oxygenation levels in the brain. When neurons become active, they require more oxygen, increase in blood flow to the active regions, which can be detected by fNIRS. The technique works by shining near-infrared light through the skull, and the changes in light absorption caused by the varying levels of oxygenated HBO and deoxygenated hemoglobin HBr are recorded. As shown in the graph, these neural activity, allowing us to map which regions of the brain are engaged during different tasks. fNIRS has several advantages, including its portability, safety, and relatively low cost, which makes it ideal for use outside the lab. The image in the bottom left shows a typical fNIRS setup, where the sensors are to monitor brain activity. This setup is especially valuable in cognitive neuroscience research and is used in clinical environments, such as during rehabilitation, where real-time brain function can be monitored. The DOT, diffuse optical tomography, image reconstruction shown in the bottom center depicts the process of mapping the data collected from multiple sensors. This method involves high-density imaging arrays, with measurements taken at different distances, to improve the resolution of the brain activity map. Forward light modeling and sensitivity profiles are used to refine these images, helping us better understand how brain regions respond to cognition. Overall, fNIRS provides a powerful, non-invasive method for studying brain function, both in the lab and in real-world environments. It is increasingly used in a variety of settings to monitor brain activity in individuals during different tasks or conditions. In this slide, we delve into positron emission tomography, or PET, a technique used to measure brain metabolism. The process begins with labeling, where a chemical molecule is combined with a positron-emitting isotope to create a PET tracer. This tracer is designed to bind to specific molecules or active areas in the body in the brain. The labeled tracer is then injected into the bloodstream, where it circulates and accumulates in regions with high metabolic activity, such as active brain areas. As the tracer accumulates, it begins to emit positrons, which collide with electrons in the body, leading to annihilation. This is the release of gamma rays, which are detected by the PET camera. The detectors in the camera capture these gamma rays in two opposite directions, which allows us to pinpoint the exact location of the metabolic activity. The signals are processed from multiple channels and combined to create a detailed image of brain activity. The data processing unit, where it undergoes image reconstruction. The reconstructed PET image shows areas of the brain with high or low metabolic activity. This helps identify regions that may be overactive or underactive, which is particularly useful in diagnosing conditions like Alzheimer's, Parkinson's disease, and brain tumor. PET provides valuable insights into both the structure and function of the brain, offering a unique look at brain activity in real time. In summary, PET is an invaluable tool for understanding brain function and diagnosing neurological diseases, providing essential information about brain metabolism and blood flow. In this slide, we focus on single-photon emission computed tomography, SPECT, a technique that is similar to PET but uses a different approach. SPECT is used to measure blood flow in the brain rather than metabolic activity. The process begins when a radioactive tracer is injected into the bloodstream, as shown in the diagram. The tracer emits gamma rays that travel through the body, and these rays are detected by a rotating gamma camera. The camera captures the gamma rays from various angles, providing the data needed to create detailed 3D images of brain activity. The SPECT detector captures the emitted gamma photons and the system's electron signals. The image on the right shows how the scintillation photons are captured and converted into signals by the detector's light guide and photomultiplier tubes, PMTs. The energy discriminator then helps refine the data, distinguishing relevant signals from noise, and the display monitor shows the final image of the gamma emitter distribution. SPECT is particularly useful in clinical settings to diagnose conditions like epilepsy, stroke, and dementia. It helps doctors visualize abnormal blood flow in specific regions of the brain, which is crucial for diagnosis and treatment planning. By providing valuable information about the brain's vascular health, an essential tool in both diagnosing and monitoring neurological diseases. In this slide, we examine the reconstructed images of various brain imaging modalities and how each technique processes raw data into valuable brain images. The comparison table at the bottom offers a detailed look at key characteristics of each method, providing insights into their spatial resolution, temporal resolution, and the activity they measure. On the left side of the slide, we see images from SPECT and PET. These techniques measure metabolic activity in the brain. The raw data from gamma ray emitters is reconstructed into images, as seen in the PET image, which highlights metabolic brain activity. SPECT similarly focuses more on blood flow. PET has a higher spatial resolution, 4 millimeters, compared to SPECT, 2 to 3 centimeters, and it measures metabolic activity, unlike SPECT, which primarily measures blood flow. Moving to the fMRI image, we see a technique that uses near-infrared light to measure change in concentration, related to changes in blood oxygenation during brain activity. The spatial resolution of fMRI ranges between 10 to 30 millimeters, and its temporal resolution is about 20 milliseconds, making it suitable for measuring hemodynamic activity in real time. This technique is particularly valuable and non-invasive nature. fMRI and MEG images, which are at the center, show high-resolution brain images and capture dynamic brain activity with impressive precision. fMRI has excellent spatial resolution, 2 to 3 millimeters, and measures hemodynamic activity, changes in blood flow related to neural activity. Its lower temporal resolution of 1 second compared to MEG, which captures the magnetic signal generated by neuronal activity with a spatial resolution of less than 1 centimeter and a temporal resolution of less than 1 millisecond. MEG is ideal for studying real-time brain dynamics, like sensory processing, with its high temporal precision. We have EEG, which provides the electrical signal directly from the brain. EEG has the highest temporal resolution of less than 1 millisecond, making it invaluable for studying fast brain processes like seizures or real-time cognition. However, its spatial resolution is lower, at 2 to 3 centimeters. It covers cortical brain regions, as shown in the image. In summary, each of these modalities has unique strengths and trade-offs. EEG and MEG provide unmatched temporal resolution, allowing for real-time brain activity mapping, but they have limited spatial resolution compared to fMRI and PET. Offers high spatial resolution and is ideal for studying brain structure and function in detail, but its temporal resolution is slower. fNIRS provides a balance with good portability and moderate spatial and temporal resolution, while PET and SPECT excel at measuring brain metabolism and blood flow, making them useful for clinical applications diagnosing Alzheimer's or tracking cancer activity. To conclude, functional brain imaging technologies, especially those involving electromagnetic neurotechnologies, have revolutionized our understanding of the brain. From mapping real-time brain activity with EEG and MEG to visualizing brain metabolism with PET and SPECT, each technique offers a unique lens into the brain's. As the technology behind these imaging techniques continues to advance, we can expect even more powerful tools for diagnosing and treating neurological conditions, as well as furthering our understanding of how the brain processes information. Thank you for watching, and stay tuned for more on the future of brain imaging and neurotechnologies. Welcome to this in-depth exploration of electromagnetic neuromodulation and its diverse range of applications. Over the course of this presentation, we will take a detailed look into the various brain stimulation techniques and the groundbreaking technologies that are shaping the future of neurotherapy. These technologies hold the potential to understand and treat brain disorders. We begin by discussing two widely researched and applied non-invasive brain stimulation techniques: repetitive transcranial magnetic stimulation and transcranial direct current stimulation. Both methods are used to modulate neural activity, offering an effective way to treat various neurological conditions without the need for surgery or implantation of devices. These techniques work by either applying magnetic pulses, RTMS, or low electrical currents, TDCS, to specific areas of the brain, influencing brain function and improving symptoms in patients with conditions like depression, chronic pain, and among others. As we progress through the presentation, we will also explore more invasive and emerging techniques such as deep brain stimulation and the cutting-edge field of brain electromagnetic implants. These advanced approaches, while more complex, offer the potential for personalized treatment and real-time adaptation, providing patient-tailored interventions for serious neurological conditions such as Parkinson's disease and epilepsy. In addition to traditional therapeutic techniques, we will look at how these innovations are converging with modern technologies to enhance brain health and even interact with brain-computer interfaces. These tools represent a transformative shift in treatment and rehabilitation for patients suffering from brain disorders. This slide introduces the electromagnetic spectrum, which showcases the range of frequencies used in neuromodulation therapies. Electromagnetic fields can vary greatly in frequency, from very low frequencies to the high frequencies associated with microwaves. We begin with the static field, a type of electromagnetic extend up to an extraordinary wavelength of 1.5 million kilometers. This field, although not commonly used for therapeutic applications, represents the lower end of the electromagnetic spectrum. Moving upward in frequency, we reach the extremely low frequency range, which operates around 50 Hz, with a wavelength of 500 kilometers. As we continue up the frequency ladder, we enter higher frequency ranges such as VLF, very low frequency, and radio frequency, progressing to microwave frequencies around 3 GHz with wavelengths as small as 10 centimeters. The relationship between frequency and wavelength determining how electromagnetic fields interact with biological tissues. Lower frequencies, such as those in the ELF range, are generally used in non-invasive therapies like RTMS and TDCS because they can penetrate tissues more effectively without causing harm, whereas higher frequencies, in the RF and microwave ranges, used in treatments such as hyperthermia for brain tumors, where they are used to heat targeted tissues to therapeutic temperatures. In this slide, we dive deeper into the non-invasive electromagnetic neuromodulation therapies. These include two prominent techniques, TDCS and RTMS. Transcranial direct current stimulation involves the application of a low-intensity direct current to the scalp. By using electrodes placed, this method modulates the electrical activity in the brain. TDCS has been shown to improve cognitive performance, reduce symptoms of depression, and promote brain plasticity, making it a promising tool for treating a variety of brain-related conditions. This technique is widely used in clinical trials and has received growing potential in neurological rehabilitation. Repetitive transcranial magnetic stimulation works by delivering magnetic pulses to the brain, which induces small electrical currents within the targeted neural regions. RTMS is particularly effective in treating depression and has been shown to help patients who have not responded to traditional medications. It is also being explored for other conditions like anxiety disorders, stroke recovery, and chronic pain management. Both TDCS and RTMS represent the forefront of non-invasive treatments that enable physicians to modulate brain activity with precision, offering alternatives to more invasive procedures. The focus of this slide shifts to deep brain stimulation, DBS, a procedure that involves the implantation of electrodes in specific areas of the brain to send electrical impulses that can modulate brain activity. DBS has been used for decades in the treatment of Parkinson's disease and essential tremors, and its applications are expanding to disorders such as obsessive-compulsive disorder, OCD, and depression. In addition to DBS, we also explore the exciting potential of brain electromagnetic implants. These implants, such as the responsive neurostimulation, RNS, system, represent a growing area of interest in the field of brain-computer interface. RNS systems are designed to detect abnormal brain activity in real time and deliver corrective stimulation to prevent seizures. Unlike traditional DBS, RNS systems are designed to adapt based on the patient's unique brain patterns, offering a personalized approach to treating neurological disorders. These technologies are the future of closed-loop systems, where the brain and implant communicate directly to optimize therapy. This real-time adjustment provides a tailored treatment experience, which is particularly valuable for conditions that require dynamic modulation of brain activity. In this slide, we delve into the cutting-edge research surrounding brain-computer interfaces, BCIs. The fully implantable wireless brain-computer interface is a major milestone in this field. These systems enable seamless communication between the brain and external devices, without the need for bulky external equipment. Using the power of wireless technology, BCIs have the potential to restore lost functions in patients with neurological disorders, such as those with spinal cord injuries, stroke, and neurodegenerative diseases. This advancement paves the way for real-time brain monitoring, the development of neuroprosthetics, and even direct brain contrasts, offering exciting new possibilities for neurorehabilitation and the enhancement of human capabilities. Moving on, we explore brain hyperthermia treatment, a novel therapy used in the treatment of brain tumors. The concept behind hyperthermia is to use heat to damage or destroy cancer cells, which are more sensitive to temperature changes than normal tissues. This slide presents a study on hyperthermia treatment planning, which includes spinal fluid convective flow to better manage the temperature distribution across the brain during treatment. By controlling the temperature precisely, we ensure that the tumor is targeted while minimizing the risk of damaging healthy brain tissue. This technique is a promising complement to other treatment modalities like radiation therapy and chemotherapy being actively researched to improve outcomes for patients with brain tumors. In conclusion, the field of electromagnetic neuromodulation is evolving at a rapid pace, with new techniques and technologies offering hope for patients with various neurological disorders. From non-invasive therapies like RTMS and TDCS to more advanced approaches like DBS and brain electromagnetic implants, these shaping the landscape of neurotherapies. The integration of implantable devices with non-invasive methods is opening up exciting new possibilities for personalized and adaptive treatments. As we look to the future, we are excited about the potential of these technologies to improve the lives of millions of people worldwide, offering new hope for brain-related conditions. Thank you for your attention, and we look forward to the continued advancements in this groundbreaking field. Welcome to this part of the Electromagnetic Neurotechnology video series, where we will explore the latest advancements in neurotechnology devices. This section will cover a range of technologies designed to enhance, interface with, or even replicate brain functions. We will begin by discussing brain-supporting technologies such as virtual reality, VR reality, AR, which enhance sensory perception and cognitive capabilities without directly interfacing with the brain. Next, we will move on to neurotechnology that interacts more directly with brain functionalities, such as brain implants and brain-machine interfaces, BMIs. These technologies establish direct communication pathways with external devices, offering new possibilities for medical treatment, cognitive enhancement, and human-machine integration. Following that, we will delve into cyborg-oriented neurotechnologies, which involve deeper integration between biological and artificial systems. These advancements push the boundaries of human enhancement by merging neural activity with power. Finally, we will explore the ambitious frontier of neurotechnology, virtual brains, and mind transfer projects. These include efforts to simulate human consciousness, transfer mental states into digital systems, and create brain emulations that could potentially redefine human identity. And we begin our exploration with virtual reality, a technology that does not rely on direct neural interaction, but instead influences the brain through immersive sensory experiences. VR creates a simulated environment that stimulates the visual and auditory senses, providing an illusion of presence in a virtual world. This technology is widely used, including entertainment, education, therapy, and training. By manipulating sensory inputs, VR can alter human perception, enhance learning experiences, and even contribute to neuroplasticity by training the brain in simulated environments. Virtual reality serves as a brain-supporting device that enhances cognitive and sensory directly modifying neural structures. Visual enhancement, VR can improve spatial awareness, reaction time, and cognitive flexibility by providing controlled and immersive visual experiences. Cognitive training, applications in neurotherapy and rehabilitation use VR to assist patients recovering from neurological disorders, such as stroke. Adaptive cognitive exercises. Sensory substitution. Some VR-based technologies aim to compensate for sensory impairments by translating one type of sensory input into another, such as using tactile feedback to assist visually impaired individuals. While VR does not directly interact with neurons, its impact on neuroplasticity, learning, makes it a fundamental stepping stone toward more advanced neurotechnology. Augmented reality is a brain-supporting technology that enhances perception by overlaying digital content onto the real world. Unlike virtual reality, which immerses users in a fully virtual environment, AR blends digital elements with physical surroundings in real time. AR enhances visual, cognitive, and interactive experiences without directly aiming. It is used in education, medicine, industry, and assistive technologies to provide real-time contextual information, improve spatial awareness, and reduce cognitive load. Visual augmentation, AR, displays holograms, data overlays, and navigation cues, improving real-world interaction. Cognitive assistance, time analytics, object recognition, and interactive simulations, AR aids in learning and decision-making. Practical applications, AR enhances surgical precision, industrial training, and accessibility for individuals with impairments. Though AR does not modify neural activity, its external cognitive enhancement plays a crucial role in bridging human perception with digital. As we move deeper into electromagnetic neurotechnologies, we explore the cutting edge of brain interfacing systems, brain implants designed for both recording and stimulation. Unlike external sensors such as EEG or even invasive ECOG electrodes, these implants establish direct interaction with neural circuits, capturing and modifying with unprecedented precision. By detecting local field potentials and high-frequency neural spikes, they provide real-time insights into cognition and neural dynamics. Beyond recording, electrical and magnetic stimulation techniques enable the modulation of neural networks, offering treatments for neurological disorders and even cognitive enhancement. Further, the concept of a virtual brain emerges, where brain activity is digitally modeled and simulated through AI-driven emulation, bridging biology and computation. This shift toward neurodigital integration opens the door to even more ambitious possibilities, such as mind transfer technologies. By leveraging brain-machine interfaces and wireless neural communication, researchers are beginning to explore ways to store and process thought patterns beyond the biological brain. The prospect of brain-to-brain communication and consciousness emulation challenges our understanding of identity and cognition, hinting at a future where the human mind is no longer confined to the physical brain. As these technologies redefine the boundaries of perception, intelligence, and self-awareness, bringing us closer to an era where electromagnetic neurotechnologies reshape the very nature of consciousness. As we push deeper into the frontier of electromagnetic neurotechnologies, brain-machine interfaces, BMI, emerge as the most advanced form of neural integration, bridging the gap between biology and technology. Unlike simple implants, BMIs are full-system architectures capable of recording, interpreting, and stimulating brain activity. These systems leverage invasive and non-invasive technologies to establish direct communication between the brain and external devices, enabling complete cognitive and motor tasks. BMIs operate through sophisticated neural implants, decoding electrical and electromagnetic signals from the brain to control robotic limbs, digital interfaces, artificial intelligence. Advanced stimulation techniques allow for bidirectional feedback, enhancing sensory perception, restoring lost functions, and even augmenting human cognition beyond natural limits. By seamlessly integrating with the brain's electromagnetic activity, BMIs hold the potential to revolutionize everything from neuroprosthetics. The ultimate vision of BMI technology extends beyond assisting those with disabilities, toward a future where humans can directly interface with machines, share thoughts without words, and even merge biological consciousness with artificial intelligence. This is the foundation of an era where the brain is no longer confined to the body, but extends into the magnetic realms, redefining what it means to be human. Cyberorganisms mark a revolutionary leap in human evolution, blending biology with cutting-edge neurotechnology. These hybrid systems integrate brain-machine interfaces, artificial intelligence, and advanced robotics to push beyond the natural limitations of the human body and mind. By creating a seamless symbiosis between neural activities, cyborgs pave the way for enhanced cognition, sensory augmentation, and even direct brain-to-cloud connectivity. This transformation is not just about interfacing with machines, it is about redefining what it means to be human. One of the most ambitious pioneers in this field is Neuralink, a company dedicated to developing ultra-high bandwidth brain implants. Neural threads are designed to enable seamless communication between the brain and external devices, restoring lost motor functions, enhancing perception, and even unlocking new cognitive abilities. Neuralink's system is not merely a tool for treating neurological disorders, it represents the foundation of a future where humans can interact with technology. Looking ahead, Neuralink envisions a world where brain interfaces go far beyond medical applications. With full-brain AI integration, the possibilities extend into telepathic communication, memory expansion, and real-time access to vast digital knowledge. Imagine a reality where thoughts can be transmitted instantly, where knowledge is up consciousness, and where human intelligence is no longer confined to biological limits. This is the ultimate vision of cyborgs, a future where mind and machine converge into a new form of existence, unlocking potentials that were once the realm of science. The virtual brain represents the next frontier in electromagnetic neurotechnology, where the fusion of brain-machine interfaces and advanced neural recording techniques enables the complete digitization of the human brain. By continuously capturing and updating neural activity through brain implants and BMI systems, we move closer to constructing a full-scale biological brain. This virtual brain is not merely a static map, but a dynamic, evolving model that replicates real-time brain function, integrating both anatomical structures and physiological processes. At the core of this concept is the ability to compare and synchronize the virtual brain with its biological counterpart. By analyzing neural responses and sensory feedback, we can refine the digital model to mirror the behavior and processing patterns of the real brain. This continuous update cycle ensures that the virtual brain reflects not only the static architecture of neural networks, but also the fluidity of thought, emotion, and memory formation. This level of neural simulation lays the most ambitious goals in neurotechnology, mind transferring. A complete, real-time virtual representation of the brain is a fundamental requirement for preserving consciousness beyond the biological form. The ability to map, store, and reconstruct the entirety of an individual's neural processes brings us closer to a future where cognition can transcend, unlocking the potential for digital immortality. The virtual brain is not just an extension of neuroscience, it is the bridge to a new era of human existence in the digital. As we stand on the edge of the neurotechnological revolution, mind transferring represents the ultimate frontier, a future where human consciousness is no longer confined to the biological brain. By building upon the virtual brain, advanced brain-machine interfaces, and real-time neural mapping, we are laying the groundwork for a world where thoughts, memories, exist beyond the limits of the body. Imagine a future where the mind can be preserved, enhanced, or even transferred into new forms of existence, breaking the boundaries of life as we know it. But this journey is filled with immense challenges. The hardware, ultra-fast processors, high-fidelity neural interfaces, and human-like robotics must evolve to the complexity of the brain. The biggest question remains, can we truly transfer consciousness, or are we simply creating a digital reflection of ourselves? And how will AI shape this future? Will it enhance human intelligence or redefine what it means to be human altogether? Despite these challenges, the vision remains clear. The fusion of neural intelligence and cutting-edge technology is bringing us closer to a world where the mind is no longer limited by biology. Whether it leads to digital immortality, enhanced cognition, or a completely new form of human existence, one thing is certain, this is just the beginning of an extraordinary journey into the future. Thank you for watching. Stay tuned for more deep dives into the future of the brain, mind, and technology. Don't forget to like, subscribe, and join us on Electromagnetic Brain, Unlocking Consciousness to stay informed about the latest breakthroughs in neurotechnology.